allowing it to think out loud, the chain of thought reasoning, it does much better. I'll show you the number. But without doing that, just like asking directly, turns out 4% accurate for 4x4 and 0% for 5x5 digit multiplication. It so happens that the first 5 authors, co-authors, are all women. We didn't plan for this, but maybe that was fate. But anyhow, so the question is, does Sparks of AGI, aka GPT-4, or my favorite language models, can do multiplication or not? So we ask, and actually it kind of looks correct, but it's a little bit incorrect. At least the first digit is correct, and the last digit, usually the first digit, last digits are correct. But I'm told that you have to ask it to think step by step, right? So we do that, and there's a different number now, but it's also slightly incorrect. So if you ask this systematically, what happens is that GPT-4 can do 3-digit by 3-digit multiplication, about 60% good. And depending on how you look at it, this is like mind-blowing good, or it's a little bit worse than you may have expected. If you do a scratch pad, more like, really allowing it to think out loud, the chain of thought reasoning, it does much better. I'll show you the number. But without doing that, just like asking directly, turns out 4% accurate for 4x4 and 0% for 5x5 digit multiplication. Again, by humans, I cannot do this either, so maybe we can justify that. It's okay. We're asking too much. So I know a lot of you probably think, like, why do we even care about multiplication? So in this paper, we actually also look at dynamic programming problems and Einstein puzzle logic problem. But in this talk, I'm gonna just focus on multiplication because A, it doesn't require compositional multi-step reasoning. B, it's just easy for us to discuss and think about. And in some sense, I'm just curious, especially seeing how amazing GPT-4 is with language proficiency and being able to compose text in a way much, much better than what I'm capable of. It's just fascinating to understand where the boundaries are. So in that sense, multiplication might be interesting. But that said, never in my life did I imagine that one day I would actually write a paper focusing on multiplication so much. But let alone that some other people like it too. So Kevin Murphy said he liked the paper, despite the fact that it's just about multiplication by and large. So here's another question. But maybe GPT-4 didn't see enough of multiplication examples. So what happens if we do supervised training? So we cannot do GPT-4 scale supervised training because the API is not provided by OpenAI. But GPT-3 Da Vinci model does have API that you can pay for to do supervised training. So we train GPT-3 Da Vinci size with 1.8 million, or 80% of that example. So 1.8 million examples include all these combinations of, let's see, 1x1 digit, 2x1 digit, 2x2 digit, 3x1 digit, 3x2, up to 4x2. And then we randomly split that into 80% training and 10% for dev and test. There's a lot of examples. I mean, should be able to do in the sense, how good though? So we actually didn't know what to think of, or at least, I felt like on one hand, I can believe that this must be doable. On the other hand, I don't know. But anyway, so it's actually not very easy to train this, even to do well on the in-domain cases. Of course, out of a domain case, it gets even worse. So, but then, we thought, oh, maybe this is because of tokenization issue, because it may not know the number boundaries correctly. So what if we train GPT-2 from scratch? So we cannot do, by the way, academics don't have enough GPUs to train GPT-3 scale model from scratch, but we can do GPT-2 XL. So let's just say, don't worry about English words or any words. Only worry about tokens that are numbers. So we only have 10 tokens. Then what would happen? Do you think this is trainable or not? Just number multiplication. So I wasn't sure what to expect personally. Maybe Some of you like shake their hands and this should be impossible. So it turns out it's very hard to train GPT to excel, only using 10 tokens. It's only like 10% accurate. So there's something interesting about how pre-trained language models that have seen language does seem to perform better, despite the fact that tokenization may have not been optimal. So anyway, the tokenization in itself may not be the issue. So, okay, you wanted to see this, a Scratchpad. So we tried many different Scratchpad, the best we could. And it turns out with the Scratchpad, the GPT-4 does do so much better. So on 3x3 digit, it's 92% good. It's not perfect yet, but it's getting so much better for sure. So, but now the question is, does that generalize to a slightly longer digit? And it turns out not really. Accuracy decreases down to 4% on the longer digit. I mean, you can imagine that this should do worse, but not like that bad. It's not. I don't think these results are all that obvious to guess. So then, if you're a skeptic, then you have to do supervised training on that. But actually, before showing you that, I wanted to share a bit of this community reaction to these empirical results, because we do see messages like, transformers absolutely can learn through multi-step algorithms in context and generalize to arbitrary problem sizes. What's going on? And here's one such example that shows how to teach algorithmic reasoning using in-context prompt engineering. So we opened the paper, and it turns out their results are similar to ours in some sense, in that from here they go to here for subtraction. For multiplication, they appear to have a bigger jump. So first of all, it's not 100%. You're not going to be very impressed if I tell you I can do multiplication 80% good. But moreover, this multiplication, there's a fine line. So they also found that GPT-4 is not very good if you go beyond the 3-digit. So what they do is they dissect a longer digit down to 3x3 or less, and then sum them up. So it's not quite the same as actually being able to do 4x4 in one go. So there's some dissection that's required. But I mean, maybe that's all correct way of doing it in the end. But for the purpose of understanding what is possible and not possible, we found, at least I was puzzled or surprised even, that the numbers are lower than what I would have anticipated, considering how amazing it is with language-based generalization. So then we decided, okay, maybe we should do supervised training with the Scratchpad on GPT-3, and just curious, what happens if we do that. So, but it's very expensive. If you want to do 5x5 digit, this is, we don't have that kind of money. I can barely spend maybe that much. So I'm cheap. So that's what we tried out of curiosity. And it does really work much better, as you may have expected. It's like 96% accuracy on in distribution, but then it doesn't generalize very well on out of domain. I mean, meaning here, longer digit multiplication.
What do you mean by Scratchpad?
Oh, Scratchpad is similar to the chain of thought, but more elaborate version, where, this kind of stuff, showing exactly how to do step-by-step reasoning as few shot examples that we provide. And the thing is, this example can become a bit too long for longer digit. Anyhow, so, we were, after archiving this paper, we also wondered about grokking. What about grokking? First of all, who knows what happens if you keep paying OpenAI more money? But to the extent we were willing to pay, we didn't see that happening yet. And again, this is like a really interesting question, at least for me, that how do we know whether grokking was going to happen but didn't happen versus it's not going to happen at all? And if so, why? Like, why multiplication is fundamentally harder than language questions. I mean, I have a speculation about that, but that aside, so we found that in general, there's some what appears to be fundamental limits to at least multiplication or some dynamic programming algorithm like problems that we experimented with. I can give you a little bit more insight about what sort of errors these models, transformers make, by the way. So we can consider multiplication through a computation graph. So when you do even as simple as 2 by 1 digit multiplication, what you do is, you do multiplication of two numbers and then store it somewhere, and then you have to add, make sure that you carry a digit correctly if you need to carry anything, and then finally arrive at this. And the benefit of drawing this computation graph is that we can actually trace back what exactly was training in the training data versus in the test data. So unlike language problems in which I may or may not have, depending on which language model you want to dissect, I may not have direct access to their training data. One can only speculate. In this case, we can actually have full access to the training data, at least if we are training from scratch. So that helps. And we found that in general, the computation graph have different width and depth, of course, and the performance is exactly proportional to the complexity of that graph. So if you multiply 1,000 with 2,000, for example, that's easy because you're not actually doing multi-step reasoning. You're just doing copy and paste of numbers based on memorized shortcut patterns. So we found that it's almost like when multiplication happens, the transformers may not be doing the true entire multi-step reasoning, but rather recognition of the subgraph that was repeated so many times in the training data, and then be able to invoke that for the final answer. So we have lots of graph demonstrating how many times certain subgraph happens has to do with that portion of computation being actually correct. Maybe humans also do some of the multiplication actually this way, so who knows. I think I'm gonna skip this error type because it's more details than you want to see. I just mentioned that in the paper, we also have this appendix where we try to sketch out a theory or proof that maybe by design, there's gonna be a rapid decay with increased compositional depth. And in fact, some such, many previous papers sort of demonstrated that in different ways, but by and large, their prior work was based on weaker language models as GPT-2. So then, people wonder whether there's something so magically different about the larger scale models like GPT-4, such that some capabilities really truly emerge, and none of this may or may not be relevant anymore. So at least empirically, we wanted to see whether we can push the boundary further. Although we couldn't afford more GPU compute, so who knows what happens if somebody is willing to push this further up. Of course, you give calculator, it's going to do way better. We all know that. And maybe that's exactly the point, though. And then the curious question is it multiplication just like one weird case, or are there any other aspects of language understanding or even common sense? And I come back to this common sense problem later. I'm going to make a weird analogy to common sense later. But for now, it's a little bit, maybe, you might wonder, are these just weird edge cases? And it doesn't really matter for other kinds of language-based problems or not. So I just wanted to throw that question. I don't know the answer for sure. But it is curious why multiplication is harder. And are there other compositional tasks? So it turns out, so my colleague Ashish at AI2, and also Will Morrell, he's a PhD student at New York University, have been thinking about this from a theoretical perspective that assumes that maybe transformers has at most log n precision. So by the way, if your transformers are infinitely precise, then it's a Turing complete. But in reality, it's not infinitely precise. It has either finite precision or maybe variable length precision. But in any case, they assume, for the purpose of theorem proving, that it's at most log n, where n is the length of the context. And so, assuming that the weights are perfect, etc., they then look at different complexity class and conclude that if you do without chain of thought reasoning, so it's either encoder only or decoder only, but without allowing that to do chain of thought reasoning, then it may be like inside this TC0 class that doesn't include many seemingly simple enough polytime problems as graph connectivity, linear inequality. But in their follow-up work that might be still, they might come out soon, but they also consider chain of thought reasoning, and not surprisingly, it does enhance the capability a lot, so that to the point of maybe a lot of these are more possible with the chain of thought reasoning, whereas planning, as Intel mentioned earlier, also is outside what may be feasible. So this is sort of like upper bound results, as I understand, and maybe there's more to think about. But based on their speculation, it's not very clear whether multiplication should have been possible, but we just couldn't train it well enough, or there's some other tighter theoretical bound around that as well. So the n is the number of tokens, the size of the context. And for the size of the architecture, actually, I was curious about that too, because obviously in our experiment, the larger models are more capable. And it seems that at least, their theory doesn't touch on the size of the models yet.